I think we're recording now, right? Yeah. I'd like to make an announcement. As you know, my son is getting married on Saturday in the backyard, and I have a lot of work to do. So I am thinking of not meeting face to face tomorrow. Instead, I will post another video tomorrow morning or this afternoon about tomorrow's lecture. Would that be okay with everybody? So I will post it, and you know I am posting them on my YouTube, so you have a link to that. How many of you is checking this YouTube link? Okay. So I will be posting it on Canvas. It's a mess. It didn't work very well. So I will. So today is video 17, I believe, and tomorrow will be video 18. Okay, the one that I will record this afternoon today and will post. So therefore, we do not meet tomorrow. All right. Now that we agreed on that, we were talking about, are there any questions, first of all? Any questions? All right. So we did this Gronwall inequality yesterday. So now we're going to have corollary 5.2. It says if un less or equal to alpha times, I'm not going to list it s equal n0 to n minus 1, 1 plus beta gamma s. Sorry. This is if alpha n equal alpha and beta n equal beta are constant, then we have this one. And this is less or equal to alpha exponential x equal n0 to n minus 1 beta gamma s. So basically, the difference between Gronwall's inequality and this one, the main one, is that now we're taking the alpha and the beta to be constant. If so, then you will have this one. Now, another corollary, and that is 5.3. So alpha n equal alpha, beta n equal beta are constant. Okay. And if un less or equal to m, alpha plus beta, s equal n0 to n minus 1, gamma s us, and here n positive, then un is less or equal to alpha s equal n0 to n minus 1, 1 plus m beta s gamma s, and this is less or equal to alpha and exponential s equal n0 to n minus 1 m beta gamma s. So these are two corollaries that the proof of this follows. Okay. So all right, any questions? All right. We're gonna use these to talk about one 192, 193. Okay. Okay, remember the title of our lecture yesterday was we're gonna talk about perturbation. So basically, now we're gonna consider the time varying system xn plus 1 equal an xn with xn0 equal x0 and bigger or equal to 0, and that is 5.54. Okay, and then we perturb 5.5.4 by a matrix Bn and look at the perturbed system xn plus 1 equal an xn plus bn xn. So the matrix B is some perturbed, okay? Is a perturbation. And we're gonna look at xn0 equal x0 and bigger or equal to 0. And this is 5.5.5. Okay? Okay. So the question is, under what conditions is the perturbed system 5.5.5 is stable when the unperturbed system 5.5.4 is stable. You see, the question is, so you start with a stable system, and then you add some noise, signals have noises in them, and then under what condition does the perturbed system stay stable? Okay, so this is the idea. Any question about what we are doing? Okay. All right, so we have the following theorem. So 5.5.2. assume the zero solution or x equals 0 of 5.4 is uniformly stable. That is US. If there is a positive constant E such that S equals 0 to infinity, BS is less or equal to E, mean the summation. This is the norm. Okay? The norm at B at 0 plus the norm of B at 1 all the way to infinity is less than or equal to E, 5.56. Then all solution xn of 5.5.5 are bounded, and its zero solution is uniformly stable. Okay, so the matrix B has to be, this matrix has to converge. Okay, so we assume the zero solution of this is uniformly stable. Well, we already know what it means from the previous theorem. Then if you have a fundamental matrix, then the norm of the fundamental matrix times its inverse is bounded. So we take it from there. So this is given. All right. So that's information is given. All right. So I'm gonna all right. So here's the proof. Let phi n be the fundamental matrix solution of 5.4. Is that right? Yeah. Okay. Now, since the zero solution of 5.5.4 is uniformly stable, there is a positive constant m such that phi n, phi inverse of s less or equal to m. Okay? Well, there is a theorem that we did yesterday. So you should look at it. Because we proved if and only if. Okay. Now, by the variation of parameter formula, the solution of 5.5.5 is xn equal phi n, phi inverse of n0 x0 plus s equal n0 to n minus 1 phi n, phi inverse s plus 1, and that is bs xs. Okay? All right. So let's take the norm, whatever any matrix norm on both sides. We get xn less or equal to phi n phi inverse of n0 x0 plus s equal n0 to n minus 1 phi n phi inverse of s plus 1 bs xs. Okay? That is less or equal to m x naught plus s equal n0 to n minus 1, again m bs xs, and that is equal to m x naught plus s equal n0 to n minus 1 bs xs. Okay? Do you see Gronwall's inequality everywhere? All right. So by corollary, 5.3, we have xn less or equal to x naught e to the m s equal n0. We can go all the way from 0 to n minus 1 bs, which is less or equal to x naught e to the m summation s equals 0 to infinity bs, and this is less or equal to x naught e to the m e. Remember, this one was less or equal to e. Remember? Hence, so this shows the solutions are bound. Okay? There. This is the bound. That is the upper bound. on all the solution. Okay. Now, for uniform stability, we let epsilon positive and set delta equal to epsilon over e to the me. Then for x naught less than delta, we have, let's come back here. We have x less or equal to delta e to the me. That is, delta is epsilon over e to the me times e to the me, and that is epsilon. That's it. That shows the zero solution is uniformly stable. Okay. Any questions? All right. You see, it's interesting. So there will be some interesting examples coming up and more theorems, actually. And I am going to do proof. I'm going to do, I meant an example. Okay. So let's take a look. Consider yn plus 2 plus 1/2 yn equals 0, xn 0 equal y 0 different from 0. So if we let yn equal y1 of n, y2 of n, then we can show this is, we can write this system as yn plus 1 equal to 0, 1 minus 1/2 0 times y1 of n, y2 of n. So what I did here, basically, I took yi of n equal to yn plus I minus 1, I equal 1 and 2. That's what I did. Okay? So I use this transformation. And I'm going to obtain this. So that is of the form yn plus 1 equal ayn. Of course, the eigenvalues of A are lambda equal plus or minus 1 over the square root of 2i. Because you look at A minus lambda I, that is minus lambda 1 minus 1/2 minus lambda, and that is lambda squared plus 1/2 equals 0. So you get lambda equal to plus or minus 1 over the square root of 2i. Okay? All right. Then the magnitude, so sigma of A is 1 over the square root of 2i minus 1 over the square root of 2i, and m of sigma of a is equal to, all right, this is the magnitude, all right. So if you look at it, it is square root of 0 plus 1 over square root of 2 squared, and 0, okay, minus 1 over the square root of 2 squared. So that is 1/2, okay, 1/2, and it's less than 1. Okay. Recall, if lambda equal a plus or minus bi, then lambda is square root of a squared plus b squared. Recall that. That's what I'm using here. Okay. Um, maybe this is, did I make a mistake? This is 1 over the square root of 2. Sorry. All right. So this is 1 over the square root of 2. But they are still less than 1. Okay. All right. So hence, hence, the zero solution of xn plus 1 equal axn is uniformly stable. Okay. Is that clear? So now let's perturb our system by adding the term minus 2 over n plus 1 yn plus 1. That is, we are looking at yn plus 2 minus 2 over n plus 1 yn plus 1 plus 1/2 yn equals 0. Again, if I let yi of n equal yn plus I minus 1, I equal 1 and 2 in matrix form, we have yn equal to 0 minus 1/2 1 0, sorry, I have yn plus 1, yn plus the matrix 0, 0, 0, 2 over n plus 1, yn. Okay? Now, this is our A, and this is our Bn. There we go. Remember? So we already know the solution to that part is uniformly stable. Actually, it's more than that, uniformly asymptotically stable, but I did not discuss it. Okay? So at least I know it's uniformly stable. So let's see what is condition. What is condition 5.5.6? It says s equals 0 to infinity, bs is finite. Well, here s equals 0 to infinity, bs is s equals 0 to infinity 2 over s plus 1, and which diverge. Okay? So that diverges. So all we can say is that theorem. Which theorem did we just use? Theorem 5.52 gives no information about the solution of the perturbed system. So it gives no information. All right. So why is Bn a perturbed system, a perturbed matrix? Because the 2 over n plus 1 goes to 0 as n goes to infinity. But it doesn't go to 0 fast. Okay? Or in other words, equal that. So this is the norm of the matrix. All right. Let me get this one. All right. Any questions? So there are a lot of interesting examples and so forth. Okay? Okay, so let me see what I have here in my note. If there's anything I need. All right, I need to get some more stuff. Okay. So far, we discussed stability of linear system of the form xn plus 1 equal to an xn, or xn plus 1 equal an xn plus bn xn. I mean, here a and b can be constant matrices. Okay, so we've only discussed linear, and this is a very important. Okay. So now, in section 5.7, we consider nonlinear system and try to linearize around the equilibrium point or equilibrium solutions. Okay. So, in other words, we're gonna consider xn plus 1 equal f1 x1n xkn x2n plus 1 f2 x1n xkn to xk of n plus 1 equal fk x1n xkn. So here f1 through fk can be nonlinear. Okay. So in matrix form, okay, we're gonna consider, or in vector form, may I say, in vector form, we're gonna look at xn plus 1 equal f of xn, where x of n equal x1 to xk, and f is f1 through fk. Okay? And we're going to call this 5.71. This is section 5.7. Okay? So the idea is, to find the equilibrium solution x star equal x1 star to xk star of 5.517, sorry, by setting f1 equal x1 star all the way to fk equal xk star. Okay? So we do that, and then we can solve for them. Any questions? Okay, so to better illustrate the idea, we take k equal to 2. That is, we consider the two-dimensional system x1 of n plus 1 equal f1, x1 of n, x2 of n, and x2 of n plus 1 equal f2, x1 of n, x2 of n. Okay? And this is 5.7.2. Okay? We assume x star equal to x1 star, x2 star is an equilibrium solution of 5.7.2. All right? In other words, what I'm saying is that means f1 of x1 star, f1, x1 star, x2 star equal x1 star. This is what it means. And f2 of x1 star, x2 star equal to x2 star. This is what that means. Okay. And then we perturb the critical point, the equilibrium solution. We perturb X star by adding eta equal eta 1, eta 2. That is X, that is 1 of n equal X1 star plus eta 1 of n, X2 of n equal X2 star plus eta 2 of n. This is what it means. Okay? All right? So let's take 5 minutes break and continue and pick it up from here. All right, I'm back. So, and we're gonna do a Taylor series expansion, and this is we're gonna do Taylor function of two variables. We're gonna perform Taylor series expansion. You remember we did this for scalar function expansion of functions of two variables. Okay, so we will see x1 of n plus 1 equal to eta 1 of n plus 1 plus x1 star, and that is equal to f1 x1 star x2 star plus del f1 over del x1 x1 star x2 star plus del f1 over del x2 x1 star x2 star plus, and then I have x2 of n plus 1 equal eta 2 of n plus 1 plus x2 star plus f2 of x1 star x2 of x star plus del f2 over del x1 x1 star x2 star plus del f2 over del x2 x1 star x2 star plus all that. Okay, now this and this cancels out. Why? Because f of x1 star x2 star equal x1 star. So you bring this over here, they cancel out. And the same thing with this one. This is equal. Same thing with this one and this one. Okay? So we arrive at eta 1 of n plus 1 equal to del f1 x1 star x2 star over del x1 plus del f2 x1 star x2 star over del x2, and eta 2 of n plus 1 equal to del f2 over del x1 x1 star x2 star plus del, oh, this is f1, del f2 over del x2 x1 star x2 star. So if we let A is del f1 over del x1, B del f1 over del x2, C del f2 over del x1, and D is del f2 over del x2, then we have eta of n plus 1 equal to A eta of n, where A is A, B, C, D. Okay? You see what happened here? And eta is eta 1, eta 2. So now we're trying to analyze. You remember in the scalar we had eta is s to power n, remember? Okay. Well, here we don't have that luxury. We have a matrices. So you remember A is constant. So this is the constant matrix. And we know the stability of that system depends on the magnitude of the eigenvalues of A. Remember, we look at the spectrum. Okay? So let's see, because sometimes this is a population model. So, okay, also the matrix A is called the Jacobian matrix. The Jacobian matrix, okay? So, all right. So let's take a look at A minus lambda I. That is A minus lambda B C D minus lambda. That is A minus lambda D minus lambda minus BC equals 0. So this is AD minus A lambda minus D lambda plus lambda squared minus BC equals 0. And that is lambda squared minus A plus D lambda plus AD minus BC. Equals 0. So we need to look at the magnitude of lambdas. So it turns out okay, so if we let a P equal to A plus D and a Q is AD minus BC, then we have lambda squared minus P lambda plus Q equals 0. And lambda is B squared, okay, minus is P plus or minus a P squared minus 4 Q squared over 2. Okay? And now see the book for comprehensive discussion. And it turned out okay? So it turned out lambda less than 1, okay? If and only if, and it's strictly less than 1, a P is less than Q plus 1, which is less than 2. Okay? All right. So we have the following theorem. Okay, so I'm going to have a theorem about this one. So that is this, I called it lemma because we derived it. Lemma 5.1. Let U star V star be an equilibrium solution solution of 5.72. Then the zero solution of 5.72 is asymptotically stable if and only if the P less than Q plus 1 less than 2, this is 5.7.8, where a P is A plus D and a Q is AD minus BC. Okay, and we define them, what they are. All right. Sorry. Then U star V star this is the way I want to say it, of 5.72 is asymptotically stable if and only if. Okay, that's what I meant to say, not the zero solution. All right. Now we're gonna talk about the when we linearized here, there was a nonlinear term we did not account for, and we assume it's continuous and so forth. So I should have done an example, but I didn't. And so I'll tell you what, I'm gonna stop here for today for this video and expect from me another video. All right, I'm gonna try to finish this linearization stuff, and on Monday we will start the last chapter 6, which is a very important for some engineers. It's on Lyapunov functions for stability of systems and or control of a system, if the system is controllable or not. So Lyapunov function plays a very important role we will see that what happened here if the lambda is not less than 1. You see, this will make this condition make the lambda are less than 1. But what happened if lambdas are, if you have a 0 eigenvalue of the lambdas are equal to 1, then what happened to the whole system? In some cases we cannot tell, but Lyapunov function should be able to tell us, provided we come up with some good Lyapunov functions. So I'm gonna say bye to you for now. I will see you on Monday, but I will have another video ready for you today that should be tomorrow's lecture. Okay, thank you very much. Okay, I'm gonna stop the AI, stop recording.